Hello, this is a lecture for section 4.4, logarithmic properties. All right, let's begin with a review of several properties that we've already discussed. We have the inverse properties. We have inverse properties. That first one just says that when the base of a logarithm is the same value of an argument with an exponent on it, that will simplify to just the exponent. And then we have the other inverse property that says when we have an exponential expression and the base is the same as it is in the exponent as a logarithm, that will also evaluate to x. All right. We talked about the exponential property or the logarithmic property of exponents, very useful, which says that when there's an exponent in the argument of a logarithm, we can bring it down and we can make it a coefficient of the logarithm, or we can turn it into a product. So log base b of a to the r power can be rewritten as r times log base b of a. Okay, and then we talked about the change of base property, which is useful when we have a funky base in the logarithm, a decimal or something like that. We can change any logarithmic expression into a ratio of logarithms that is an easier base to deal with. So for example, if I had a base that was a decimal, I could then rewrite that as the common log of the argument over the common log of the base. Okay. Two new properties I want to introduce here. One is the sum of logs property. Sometimes this is called the sum product property, because this property says if we have two logarithms with the same base and we're adding them, we can rewrite that as a single logarithm, and the arguments of the sum become a product of those arguments when we combine them, right? We can use this sum of log properties in reverse as well to expand a logarithm of products into a sum of logarithms. Okay, and then we also have the difference of logs property, which says if we're subtracting two logs that have the same base, we can combine them to a single log, and the arguments of the subtracted logs become quotients. Okay, the argument of the positive logarithm will be in the numerator, and the argument of the negative logarithm will be in the denominator. All right, let's look at some examples where we would need to use the property of logarithms. These examples say to simplify, or sometimes you may see that specified evaluate, right? So if we're going to simplify log base 3 of 32 minus log base 3 of 4, probably the first step we want to take here is to combine those two logarithms by using the difference to quotient property, right? So I can rewrite that as a single logarithm with the same base, log base 3 of, and then the argument of the positive logarithm will be in the numerator, and the argument of the negative logarithm will be in the denominator, right? And then of course 32 divided by 4 is 8, so I could simplify this further and write it as log base 3 of 8. Okay. How about this one? 1/2 log base 5 of 36. Well, you might glance at that and think that, gee, that's simplified, but I think we could simplify it further. We could use the exponent property of logarithms in reverse, right? And we could bring this coefficient, right, or this product up and make it an exponent of the argument. So then we could rewrite that as the log base 5 of 36 to the 1/2 power. And of course, 36 to the 1/2 power, that's the same as the square root of 36, right? Which is going to be 6. So this would simplify all the way down to log base 5 of 6. Oops. There we go. Okay, this third one, here's a difference of logarithms. Again, we can combine that into a logarithm of quotients. This one has no base, so recall that's the common log, or the implied base 10. So this becomes the log of let's see, the argument to the positive logarithm is the numerator. So it becomes the log of 12 x to the fourth divided by the log of 4x. The argument to that negative logarithm goes in the denominator, right? And then that argument will simplify, right? That'll simplify to the log of 12 divided by 4. That's just 3. And then x to the fourth divided by x, that'll be x cubed. All right? Now, let me ask you something. Can I take that 3 and bring that down and make that a coefficient to the logarithm? It's a little bit of a trick question. The answer is no, because that exponent only applies to the x. It doesn't also apply to this 3. Okay? If the exponent had been outside here, I could have brought it down. All right, look at the next one. This is a sum of logarithms. I could combine that into a logarithm of products. But what do I do about these coefficients here, right? Go back and look at this property. The pattern doesn't show us there's any coefficients, right? But what I do with them when I'm combining the two logs. So I need to get rid of those coefficients first. And I can do that with the exponent property of logarithms. Let me just bring those up and make those coefficients be exponents. So then I can rewrite this as the log of x cubed, right, plus log, that's common log again, of x squared, and then I have to raise that to the second power, right? When I raise x squared to the second power, I mean, I could just put another set of parentheses in there and go like that. That'd be fine. Okay, and then that would simplify. When I raise a power to a power, I multiply those exponents. So let me just rewrite this. This then becomes the common log of x cubed plus the common log of x to the fourth. All right, now I can combine those into a single logarithm. It's going to be the common log of x to the third times x to the fourth, right? Because they're sums, they will become products, right? And then I can simplify that argument a little bit further. And this would become the log of, what is x cubed times x to the fourth? When I multiply exponential expressions, I add the exponents. If the bases are the same, of course. So this then becomes the common log of x to the seventh. All right, there's one more here, some coefficients, so let's move those up first. We can't combine logarithms that have coefficients. All right, let's rewrite that then. That's the log of x squared plus the log of y to the 1/3 power, all right, minus log z. Okay, now that there's no coefficients, I can combine them. I have 3 logs here. Does it matter? No, I'm going to do the same thing here as I would. I could have 5 logs if I want to, 7, 20, an unlimited number of logs. I'm just going to combine them, and any positive logarithms will have arguments that become a product in the numerator, and any negative logarithms will have products in the denominator, right? So when I combine this to a single log, it becomes the log of, okay, the log of x squared, that's a positive logarithm, so x squared will go up here in the numerator. Another positive logarithm, log y to the 1/3. So y to the 1/3 will become a product in the numerator. Okay, then I have a negative logarithm, so that z is going to need to go down in the denominator. All right, very useful properties. Let's look at using them in reverse. Say we have a rather complex argument to a logarithm and we want to simplify it. So we could expand a single logarithm into multiple logarithms by using the sum to product property in reverse and go product to sum, or the difference to quotient property in reverse and do quotient to difference. All right, so in this first one, I have a common log of a to the 4th times b to the 9th divided by c to the 12th. right? To expand that, any products of the numerator are going to be positive logarithms, right? So I'd expand this log of a to the fourth, and then it's times, here's another positive logarithm because that's a product of the numerator again. So that'll be plus common log of b to the ninth. Now c to the 12th is down in the denominator of the argument, so that will need to expand to a negative logarithm. That would be minus log c to the 12th. And I have one more step here because look, it says there should be no remaining exponents. So let me just bring down all those exponents and make them products, or coefficients, if you will. 4 log a plus, bring down that 9, that's going to be 9 log b, and then minus, bring down that 12, 12 log c. Okay. Look at this next one. It has a radical in there. And we don't like radicals when we deal with logarithms. So when we find a radical in the argument, we need to convert it to a fractional exponent. All right. So this log base 3 of the square root of 5x cubed can be rewritten as log base 3 of 5x cubed raised to the 1/2 power. Right, because the square root is the second root and everything in there would be the first power. All right, so I can simplify this now a little bit. I'm not supposed to have any remaining exponents. One thing I could do is I could distribute this 1/2 power to both products in that argument. But you know what I think I'm going to do? I think I'm just going to, since the 1/2 power applies to the entire argument, I think I'm just going to bring that down now. I think I'm going to bring that down first. And then I'll rewrite this as 1 times the log base 3 of 5x cubed. All right. Now I can expand this single logarithm into 2 logarithms, right? Because this is a 5 times x cubed, right? So I can expand that logarithm of products into a sum of logarithms. Now, the sum, that whole sum is going to be multiplied by 1/2 though, so let me get that 1/2 out there and add some parentheses. So this will then become 1/2 log base 3 of 5 plus log base 3 of x cubed. All right, and then there is one more step because I'm not supposed to have any remaining exponents. I have this one last exponent I need to bring down. It's only going to apply to that last logarithm. So I can then rewrite this as 1/2 times log base 3 of 5 plus 3 log base 3 of x. And then if I wanted to, I could distribute that 1/2, or I could just leave that as it is. Okay, maybe I'll distribute it. 1/2 log base 3 of 5 plus 1/2 times 3 is 3/2 log base 3 of x. All right, there's one more here. Note the difference. Note the difference between these two. And in the example we just finished, the entire argument was a radicand, right? Or the entire argument was under the square root. Here, it's just the y to the 8th that's under a radical, and it's actually the 9th root of y to the 8th. There's a multiplication. Maybe we should add a set of parentheses there. All right, so let's see. I think probably the first step I want to take here is it's x times the 9th root of y to the 8th. So let's expand that first. This time I'm going to expand that first because I can't bring down these exponents because they're different. They apply to different things. The exponent of 4 only applies to the x. I could rewrite first. Well, maybe I will do that. Get rid of that radical sign. Let me rewrite this. It's the natural log of x to the 4th times and this will be y to the 8/9 power, to the 8/9 power. Okay, remember you're converting radicals to fractional exponents. You can Google that if you've forgotten some of those rules. All right, now I can expand this and write this as the natural log of x to the 4th plus, because these are products in here, the natural log of y to the 8/9, right? And then lastly, I can bring down those exponents. Finally, this will be 4 times the natural log of x plus 8/9 times the natural log of y. Okay. All right, so there's these two new properties of logarithms that we can use in conjunction with those previously discussed. Now let's take a look at solving exponential equations perhaps using some of these new properties. All right, look at this first one. 2 raised to 2x minus 5 power equals 7 raised to 3x minus 7 power. All right, so what do I need to do? I want to solve for x. I've got to get that variable out of the exponent. There's two ways to get a variable out of the exponent. One way would be to convert the exponential equation to a logarithmic equation. But the problem with that is it's only going to get one exponent out because we have two. The second way, and the easier way here, would be to take the log of both sides of the equation, right? So let's do that and rewrite it. We'll take the log of both sides of the equation. I'll just use common log. So then we'll have the log of 2 raised to the 2x minus 5 power equal to the log of 7 raised to the 3x minus 7 power. Okay, and I'm able to do that right off the bat because I only have one exponential equation equal to another exponential equation. If I had more than 2 terms here, I wouldn't have been able to do that. But I don't have 2 terms. I mean, I do only have 2 terms. Now that they're both sides are written as logarithms, I can bring down that exponent and I can get that variable out of the exponent. All right, so we'll now rewrite this. And actually, maybe we'll go up here to rewrite it. It will be 2x minus 5, that's that exponent coming down, right, times log 2. And then that's going to be equal to that 3x minus 7 times log 7. All right, now that I've got that variable out of the exponent, I'm just going to use algebra to solve for that variable. Okay, so I'll need to simplify first here. I'll need to simplify because I've got some parentheses to deal with. So I could punch in my calculator and see what the logarithm of 2 is. It's probably a very ugly decimal that goes on forever and ever. And I really don't want to have to round decimals until the very end when I'm doing calculations with logarithms, because it can change my value significantly if I round my decimals too early in the process. So I'm going to leave that logarithm as the expression log 2, just knowing it's a number, all right? And I'm going to distribute log 2 to both terms in the parentheses there. So then I'll have 2x times log 2 minus 5 log 2. And that's going to be equal to, I'm going to do the same thing over here, I'm going to distribute that log 7. So that'll be equal to 3x log 7 minus 7 log 7. Okay, now x is what I'm solving for, so I'm going to need to get those x terms on the same side of the equation. I think I'll move to the left. So let me then subtract this 3x log 7 from both sides. And this 5 log 2, that negative 5 log 2, that doesn't have an x in it. So let me move that over there with the other logarithm that doesn't have a variable. So let me go ahead and add 5 log 2 to both sides. All right, so then what do I have left? Let's see. 2x log 2 minus 3 log 7. Well, I can't combine those terms, so let me just write it out. 2x log 2 minus 3x log 7. These add out. And that's going to be equal to, let's add out, negative 7 log 7 plus 5 log 2. All right. Okay, now I need to solve for x. I can't combine these terms. I can't combine them because I don't really know exactly what those values are. So probably the easiest thing to do is let's just factor out that x. All right, let's factor it out. So when I do, what's left is 2 log 2 minus 3 log 7. Of course, it's still equal to negative 7 log 7 plus 5 log 2. All right. Then, solving for x, all I need to do is divide both sides by this 2 log 2 minus 3 log 7. And there's my value for x. Now, if I want, I can put that in my calculator and round my decimal. All right, so let's see. What is the numerator? Let's put it in parentheses. The numerator is negative 7 log 7. I used common logs, so that log here will be nice. Okay, negative 7 log 7 plus 5 log 2. All right, that's the numerator, so let me close that off with a parenthesis. And then it'll be divided by, and here's the denominator. I'll put that in parentheses as well. The denominator is going to be 2 log 2 minus 3 log 7. All right, and let's see what that is. Looks like that value is approximately 2.2814. We'll round it to 2 decimals. Okay. Look at this next example here. Similar to the one we just solved, it's an exponential equal to an exponential, but the differences are crucial here. The differences are, look, these two exponential expressions have coefficients. How do I get rid of them? I can get rid of one of them by dividing both sides by that coefficient. Like I could divide both sides by 20, and then I wouldn't have one on the left, but I would still have one on the right. And that's still a problem, isn't it? Because I cannot take the log of both sides if I have coefficients there. So what else might I do? Well, when I look at this, I can see that the exponents happen to be the same. Since the exponents are the same, then maybe I could divide both sides by one of the exponential expressions and combine them. Look, if I divide both sides by, let's divide both sides. It doesn't really matter which exponential I use, but I think I'll just divide both sides by 1.13 raised to the z power. Oops. Okay, so then this part divides away on the right, and let me just rewrite that. I now have 20 times, and because this is the same exponent, I can just write it as a fraction. 1.07 divided by 1.13 raised to the z power. Of course, that's just going to be equal to 8. All right. So now I can get rid of this coefficient, right? Because I only have one exponential expression. So I could divide both sides by 20. And then what I have left is this 1.07 divided by 1.13 raised to the z power. Okay. And it's going to be equal to 8 divided by 20, which of course would reduce, wouldn't it, to 4/5. But I can go ahead and write that, I guess. All right. I do with this. Well, I can solve this in one of two ways. right? I can solve it in one of two ways. Let me go ahead and erase so I have a little bit more space, because I do want to rewrite this so we can make sure that we see the pattern clearly. That should give us enough space. All right, let me just rewrite the equation that I have now. It's the 1.07 divided by 1.13, and all of that is raised to the z power, and that's equal to 4/5. Okay, so the two methods now, the two things that I could do at this point, I could take the log of both sides, because then I could bring down that z. Nothing wrong with that. I also could convert this to logarithmic form, but I would have a very unusual base on my logarithm, right? The base, it would be log base 1.07 divided by 1.313 of 4/5 equals z. And then I would just have to evaluate it. So either method, it doesn't really matter. Took the log of both sides up above. So this one, maybe I will go ahead and convert that to log form, right? Let's look at it that way. This then becomes the log of, and the base is very strange, right? Log base 1.07 divided by 1.13 of, what's my argument here, 4/5. Okay, then that equals z. Now, many of your calculators will evaluate that for you directly. If they don't, you can use your change of base formula on it, right? You can use your change of base formula. Let's go ahead and use that change of base formula so you can see how that would work. With the change of base formula, let's see, we'll change it to common log. This then becomes a ratio of logs. It'll become the common log, or just log. And I'm using common log. I could use natural log as well. Both of those have keys on all scientific calculators. That's why I've chosen it. Become the common log of, what's up high stays up high. So the 4/5 will be in the numerator over the log of, and the base will be in the denominator. 1.07 divided by 1.13. All right, now that's something that every calculator can calculate. Let's see what that value approximates to. So we have the common log of 4/5. Calculator doesn't want to turn on. There it goes. All right, so we have the common log of 4/5 divided by, that's 4/5, the common log of a ratio. Let's see, 1.07 divided by 1.13. And that approximates to 4. Let's just use 2 decimals. Let's round that to 4.09. All right. Now you wouldn't have had to use the change of base formula. If your calculator does it, and I believe my software, my online calculator, I believe it does have, let's see, where would that be at? Under math, my log base function. See if I can get down there to it. There it is. My log base function. So I'd say log base, and then I go ahead and put my ratio of 1.07 divided by 1.13. That's just the base there. All right, then use this arrow key to move over for the argument. In the argument, I'll put 4/5 or 0.8, but never really simplify. Just put the whole thing in there. And you'll see I get the same exact value. So, all right. Let's see, one more slide here. Let's look at solving some logarithmic equations using these properties of logarithms. All right, so we're going to solve for the given variable. Looks like it's always x. That's good. So what are we looking at this first example? Log base 3 of 2x plus 4 equals 2. Okay, I've got a sum happening that's in the argument of the logarithm. So there's nothing I can do with that. Look down here, I've got a sum of some other things. Here's a sum of logarithms. I could have combined those. Can't do that here. So I think what I want to do in this case to solve this guy, I've got one logarithmic expression. I think the easiest thing here is going to be to convert convert this logarithmic equation over to exponential form, right? When I have one logarithmic expression. So when I do that, then I have 3 squared. It's going to be equal to 2x plus 4. Right? Well, 3 squared, of course, is 9. Right? So I'm solving for x. If I just subtract 4 from both sides, let's go up here to finish. 9 minus 4 is 5, equal to 2x, and then just divide both sides by 2. And there's my solution. X equals 5/2. Right, look at the next one down here. This has got a little bit more action going on, but I want to simplify this expression, or I want to combine like terms before I deal with the logarithm, right? So I've got 4 times natural log of 5x plus 5 equal 2. Let's see if we can just subtract that 5 from both sides. Let's move that over to the right, because that's a constant over there anyway, right? And then I'll have 4 times the natural log of 5x is equal to -3. Okay, so now this pattern is looking similar to the one we just solved, except it has a coefficient, right? I'm tempted, I want to convert this over to exponential form, but I can't yet because I need to get rid of the coefficient. So since it's a logarithm, let's go ahead and bring up that coefficient. Now it's going to apply to both the 5 and the x in that argument there, so I want to be careful with that. So let's see, this will be the natural log of 5x, and then all of that is being raised to the 4th power. Okay, all of that is being raised to the 4th power. And then that, of course, still equals -3. All right, now I can convert that over to exponential form if I want. Remember that the natural log is just log base e. Let me just rewrite it that way. Log base e of 5x to the 4th power equals -3. Then, when I convert that over, I can see that, let's write it over here, e to the -3rd power is equal to 5x to the 4th power. All right, so we're solving for x. It's in there with the parentheses. So I think I'm going to need to apply that exponent to both. So I can drop the parentheses. Then I'll have e to the -3rd power equal to 5 to the 4th power times x to the 4th power. All right, what is 5 to the 4th power? Well, I don't know. I don't really need to know. I'm going to leave it like that first. It's just a value. I'm solving for x. So let me divide that 5 to the 4th power away. Let's divide both sides by that. Go up here to finish. So then I have e to the -3rd power over 5 to the 4th power equal to x to the 4th power. All right, this e to the -3rd, that's kind of bothering me. I kind of want that to be a positive exponent, so I think I might bring that down. Write this as 1 over e cubed 5 to the 4th equals x to the 4th. All right, does that make sense? Now all I need to do is take the 4th root of both sides, or raise both sides to the 1/4 power, and I will have my answer. All right, so 1 to the 1/4 power, of course, is just going to be 1, so let me just do 1 over. And then down here, I'll have, let's put them together, e cubed 5 to the 4th equal to x. All right, and that can simplify a little bit more, because 5 to the 4th raised to the 1/4 is just 5. E cubed raised to the 1/4 is e to the 3/4. So I could simplify that a little bit further and write that as 1 over e to the 3/4 times 5. Probably put the 5 in front when I did that. Okay, and now if I want to approximate that, I can stick that in my calculator and find that approximate value. Software always turns itself off when I minimize. There it is. So what do we have? 1 divided by, I'll put some parentheses for that denominator. All right, it's going to be 5e to the 3/4. So let me say 5 times, let's use my e to the x key. That's second ln. All right, e to the, and then that exponent is 3/4. So 3 divided by 4. All right. Looks like that's approximately 0.0945. Approximately. All right, that ends the lecture on section 4.4.